Welcome. This is the video version of the lecture corresponding to Chapter 2, Sections 2 and 3 of the book Basic Sentential Logic and Informal Fallacies. This is for Phil 10 at UCSD. In this video, as I said, I'll be discussing Chapter 2, Section 2, which is on constructing truth tables, and then also Chapter 2, Section 3, which is on categorizing statements as either tautologies, contradictions, or contingencies by using truth tables. Okay, so first up, section 2.2, constructing truth tables. Well, we just finished in the last video covering section 2.1 the truth functions of the various operators. So conjunction, disjunction, conditional, biconditional, negation, and we specified those in what were in fact truth tables. So if you'll recall, we had a little grid that was used to display the truth function of conjunction, for example. What we're going to do now is essentially the same thing. We're going to construct a grid where we specify the truth value of a compound statement, like the one here, as a function of the truth of its components, and ultimately all the way back to the atomic statements that compose it. So here's how we're going to construct a truth table. Take our compound statement like this. It's a disjunction, P and Q, or Q if and only if P. We're going to construct a grid now, and we need to know how many rows and how many columns to make on that grid. First up, the number of rows. The number of rows we're going to need is 2 to the n power, where n is the number of atomic statements involved in our compound statement. How many atomic statements do we have in this? Well, you might say it's 4, maybe, because we have P, Q, Q, P. If you count each one of those occurrences, you'll get 4. But that's not what we mean. What we mean by the number of atomic statements is P would just count as 1 and Q just counts as 1. So here we have 2 atomic statements, P and Q. P is used twice and Q is used twice, but there's still only 2 atomic statements involved. If we had P, Q, and R, that would be 3. P, Q, R, and S would be 4. So here we have 2 atomic statements. And 2 to the second power, 2 squared is 4. So we're going to need 4 rows. We're also going to add 1 row on the top where we will write the statements themselves. So really it's 2 to the n plus 1. You'll see what I mean by that in a moment. But officially it's 4 rows. Now we're going to need to know the number of columns to make in our truth table. We're basically going to need 1 column for each statement that's involved in the construction of the compound statement. Okay? And I've listed them here. Altogether, there's 5. But the whole compound statement involves P, Q, the conjunction P and Q, the biconditional Q if and only if P, and then the entire statement itself, the entire disjunction, P and Q or Q if and only if P. So we'll need 5 columns, 1 column for each of those. So here's what the grid looks like. You'll notice that I made the width of the columns a little bit wider as we went from left to right. That's because the statements we'll be writing in those columns are going to get bigger as we go from left to right, as you'll see. As a convention, so we have 4 rows and 5 columns. We're just going to, if we have to refer to anything, we'll number them this way. That's going to be row 1, 2, 3, 4. The top one doesn't count. We're going to be writing statements in that. And column 1, column 2, column 3, column 4, column 5, and so on, depending on how many columns there are in our truth table. In the first columns, on the top row, the unofficial top row, what we're going to do is put the atomic statements in alphabetical order. Okay? Why do we need to put them in alphabetical order? Well, in general, if you put them in something that's not alphabetical order, you will still get the right answers, so to speak, in the sense that you're still going to categorize tautologies as tautologies, and you'll still get the same answer if you're assessing argument validity. It'll just have the effect of shifting the rows up and down and around. But for purposes of this class, put them in alphabetical order, because in some cases there will be multiple choice questions of the form, you do a truth table and the question is, what letter appears in row 2, column 3? And in order to get the right answer for to that question, you have to do the truth table with the atomic statements in alphabetical order. So that's why that's important. Okay, so first we put the atomic statements alphabetical order. Next, we're going to fill out the truth columns for the atomic statements. And the truth columns that just means the column of T's and F's that are underneath the statement. That is the statement's truth column. So the truth column for P is true, true, false, false. For Q, it's true, false, true, false. How do you know how to get all of the combinations? That's our goal. We want all of the combinations of truth values of our atomic statements. Well, if you only have 4, it's pretty easy. They're both true, first true, second false, first false, second true, both false. But if you get 8, 16, 32 rows, it's going to start to get difficult for you to just keep in mind and check by looking if you've got all the possibilities down. Here's a recipe that you should use to ensure that you've got a good truth table that has all of the possibilities. What you do is in the first column, in this case it's P, column 1, you make the top half of that truth column T's and the bottom half F's. So the column has 4 rows, so we're going to make the first 2, that's half, T, and the next 2, F, the bottom half. Then you move over one column and you alternate by T's and F's in groups that are half as big as the group you just alternated with. Well, we just alternated with groups of 2, so the next column I'm going to alternate with groups of 1. So TF, TF. And if you've done it right, the column where you're alternating by groups of 1 is going to be this column of your last atomic statement. So here's a way to think of it. In column 1, top half T's, bottom half F's. Move over one column, alternate by T's and F's with groups half as big. If we had 16 rows with 4 atomic statements, for example, in column 1 we'd have 8 T's and then 8 F's, top half, bottom half. Then we would move over one column and alternate with groups half as big. So instead of 8, we'd alternate by 4s. True, 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 false, 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 true, 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 false, 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 false. Move over a column and alternate by groups half as big, in this case 2 because we just did 4, and so on. And if you follow that recipe, which is pretty easy, you will get all of the truth values. Okay, so now we've got the truth columns for the atomic statements. Now we're going to get all the compound statements going. So what I'm going to do next is in subsequent columns, I'm going to put the compound statements building up from, so to speak, the smallest to the largest, or slightly more appropriately, starting with the ones whose only components are compound, or I'm sorry, whose only components are atomic, and then slowly building up to the statements whose components are compound until you get to the biggest statement, the one we're doing the truth table for. Okay, I'll say a little bit more in section 2.4 about what kind of flexibility you have in terms of the order you do the columns in. But basically you just put them in order from smallest to largest, generally speaking. Well, what you're going to do now is then fill out the truth column for each one of the atomic statements. And how are we going to do that? Well, in this column we have a conjunction. And remember, a conjunction, the truth of a conjunction is a function of the truth of its components, the conjuncts. So if we want to know on row 1, is this conjunction true in row 1? Well, what we need to do is ask ourselves, well, what's the truth value of the conjuncts on row 1? Okay, well, let's look. On row 1, the first conjunct is true, the second conjunct is true. So that's the value of the inputs, the conjuncts. And according to the truth function, when the first conjunct is true, second conjunct is true, the whole conjunction is true. So we put a true here, a T. Okay, so that's what we're doing. We're just going row by row and then looking to see what the inputs are and then use the truth function to determine what the output is going to be. So in row 2, okay, it's a conjunction. What are the inputs? P and Q are the conjuncts. P is true, Q is false. First conjunct true, second conjunct is false. What does that function output? Well, let's take a look at the table. If the first is true, second is false, it outputs false. So I'm going to put an F here. And so on. Now we're lucky because right now this column matches exactly the column that we used in the truth table for the truth function. And that's just kind of an accident. It's a happy accident. It's not always going to do that. And we'll see in a minute a case where it doesn't. Now let's do the biconditional. It's going to be the same thing. I've put the truth function for biconditional down at the bottom just to remind you what that is. But if we go up to the first column and we ask, okay, what's the truth value of this biconditional in this row? Well, in this row, the two components are Q and P. The first component, Q, is true. Second component, P, is also true. So let's go down to the truth table. When the first component is true, second component is true, the whole biconditional is true. So I put a T. And so on. When it's false true, this is false. False true gives us false. When it's true false, it's false. True false gives us false. And when they're both false, on row 4, both false gives us true. Okay, so far so good. The last column I want to go slowly because this is the one where it deviates from the order that the truth function gets displayed in. And if you get this, and if you understand this, you'll be able to do truth tables much better, because in how we're going to determine the truth column here is really how you always determine truth columns for every statement, except for the atomic statements. Okay, so the statement in the last column is a disjunction. And I'm marking off the two disjuncts here with squares. So the first disjunct is red, the second disjunct is blue. Where do those show up on our truth table? Well, we can't do a statement until we already have its components. So those components are already on the truth table somewhere. They have to be, otherwise we can't do this. And they are. They're here in rows, columns 3 and 4. Right? The first disjunct is in column 3, the second disjunct is in column 4, and I've put colored blocks around those to indicate that. Now I'm going to remind you of the truth function for disjunction, and that's right here at the bottom. Okay? So let's start filling out this column. Let's look at row 1. So in row 1, these are our inputs. Red, remember, is for the first disjunct. So the first disjunct is true, second disjunct is true. So if we look down at the truth table, that corresponds to this row. First disjunct true, second disjunct true. And what we can see is that in that condition, the output is true. So I'm going to just put a T right there. Okay, so far so good. Now let's move down and do the next row. The next row, which is row 2, the first disjunct is false, second disjunct is false. So now let's go consult the truth function. When the first disjunct is false and the second is false, that's here at the bottom, it outputs false. So I'm going to put an F there in that column, row 2 of the truth column. Let's move on to row 3. In row 3, both disjuncts are false. First and second are false. Well, that's down here at the bottom again. And according to the table, the output is going to be another false. Boom. Okay, and finally, let's go to the bottom row, row 4. Here the first disjunct is false and the second is true. Okay, let's find that combination right here. First is false, second is true, and according to the truth table, the output here is true. Okay, so now that's our truth column. Now you can see it's apparent here that this pattern is not the same as this pattern, right? This isn't just true, 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 false. Because when you're filling out columns, what you're not doing is just associating disjunction with a true, 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 false pattern. You're associating disjunction with this input-output function. Okay? If in your truth table, both statements are always true, it's always going to output true during the whole column, right, for instance. So you have to consult the table to determine what these values are. So this is what the truth table would look like. Okay, let's move on to another example. Here's our statement. How many atomic statements do we have in this? 2, C and D. How many statements are involved in building up from the atomic statements to the largest compound statement? Well, we have C and D, that's 2. Not C and not D, that's 4. Okay, we have not C if and only if D, that's 5. We have the negation of not C if and only if D, that's 6. And then we have the entire conditional, 7. So we're going to need 4 rows and 7 columns. And so there's the truth table that I'm going to be filling out. First up, atomic statements in alphabetical order, and filling out the truth columns for both of those. And by now you know how to do that. Now I'm going to put the rest of the statements up, building up from the ones that are constructed directly from the atomic statements, and then building all the way up to the most complex compound statement at the end. So let's start filling out the columns. Not C is easy, because that's just going to be the opposite of C, right? C is true, true, false, false, so not C is going to be false, false, true, true. In any row where C is true, that's going to switch to false, and rows where C is false, not C is going to switch to true. Very easy. In the next column, if you look over, we're going to have the opposite of D. So true becomes false, false becomes true, and so on, all the way down. Okay, that's easy. Next up is the biconditional. Not C if and only if D. What are the two components of the biconditional? They are not C and D. Remember, the easy way to do a biconditional is that a biconditional is true when the two components have the same truth value. Well, they have the same truth value on 2 and 3. Here they're both false, that's the same. Here they're both true, that's the same. On 1 and 4, they're different. Okay, so they're true on 2 and 3 because the inputs have the same truth value. False on 1 and 4 because on 1 and 4 they have different truth values. Now, the negation of not C if and only if D is easy. That's just the opposite of the input. So instead of false, true, true, false, it's true, false, false, true. Now, let's do the final conditional. What I've done here is I've marked off and indicated with a red square the antecedent of the conditional and with a blue square the consequent of the conditional. So here's the antecedent, here's the consequent, and then I've indicated where those components are on the truth table. The antecedent is here, the consequent is there. Okay, so now we're just going to go down row through row. I'll remind you of the truth function of conditional, and we're going to fill this out. Okay, so let's go to row 1. Row 1, we have a true antecedent, false consequent. So let's see where that shows up on the table. Right here. True antecedent, false consequent. According to the table, the output is F. So I'm going to stick an F there in row 1. Let's move down. In row 2, antecedent is false, consequent is true. That's going to be here. False antecedent, true consequent, and the output is true. So I'm going to stick a T right there. If we move down one more row, both are false. Antecedent is false, consequent is false. That's displayed here on this row. The output is true, so I'm going to put a T there. And finally, on row 4, we have a true antecedent and a true consequent. Oops. That is the wrong row. Sorry about that. This should be row 1 here. Let me just fix that. I'm going to move these up. Sorry. That should be there. There, everyone gets a little bonus edit. There we go. Let's do that again. In row 4, we have a true antecedent and a true consequent. That's indicated here. The output is going to be true. So here is our final truth table for that statement. And that will, getting rid of all of the extra stuff, just look like that. Okay, now that's the, if you memorize that, how to fill out truth tables with the method I just used, you will be fine and you will get all of the points on the exams. There is another approach that's a little bit faster, and I'll show you how that goes. I'll give you an example. But, and it's the approach I use. Notice that, for example, conjunctions are only true with one specific input pattern, when both inputs are true. They're false all the rest of the time, okay? So if you're doing a truth column for a conjunction, what you can do is you can just go over and find the rows that have both T. They're both T. Just look for that special pattern. The conjunction will be T on those rows and false everywhere else. So all you need to do is put a T in the conjunction where you see that pattern, and then the rest of the rows just put an F. Something similar for disjunction. Notice that disjunctions are only false with one specific pattern, when both inputs are false. So if you're doing a truth column for disjunction, just look for that specific pattern, 2 Fs, an F for both inputs. Mark an F for the disjunction on those rows, and then when you're finished with that, just put T's everywhere else. Conditionals also have a special pattern that, which is that the conditionals are only false in the specific case where you have a true antecedent and false consequent. So when you're doing a truth column for a conditional, you can just look for that pattern. Look for any row where you have a true antecedent, false consequent, mark that as F, and then when you're done, everything else gets a T. Okay, biconditionals aren't quite as easy because there isn't one kind of standout pattern that is the only one that gives you one of the letters, but they're still pretty easy. What you can do is remember that biconditionals are true when they have the same truth value. So you can just go down the 2 input columns. Wherever they're the same, both true or both false, you put a T, and then when you're done, you just stick Fs everywhere else. And negations are easy because it's just the opposite, so you don't need any special strategy for doing negations more efficiently. Okay, let's do another truth table here. This one's kind of fun. It's if not R, then R. How many atomic statements do we have? 1. And 2 to the first power is just 2. So we're going to need 2 rows. How many columns are we going to need? Well, how many statements are involved? We have R, not R, and the conditional if not R, then R. So 3. So we're going to need 3 columns and 2 rows. And we just follow the recipe. In the first columns, we stick the atomic statements in alphabetical order. Well, there's only one atomic statement, so we can just put R there, and now it's in alphabetical order. Now we fill out the truth columns for the atomic statements. We go to the first column, top half T's, bottom half F's. Well, the top half is just this one cell, so it's going to be true, false. So that's easy. Now we're going to put the more compound statements up, not R, and then the full statement, if not R, then R. Not R is going to be easy. because it's just the opposite of R. So instead of TF, it's FT. Now we're going to do the conditional. Now remember the thing I just mentioned to you. Conditional is only false with one specific pattern. So I'm going to look for the rows where we have a true antecedent, false consequent. Here's the antecedent. Antecedent is not R, and that's here. So where do we have a true antecedent, true in this column, false consequent, false in that column? Only there. So I'm going to put a false here, because that's the only place we have that pattern, and everything else is true. And boom, that's the truth table for that statement. Let's do a bigger one. This one's a little more fun because we're going to have 3 atomic statements now, and 2 to the 3rd power is 8. So we're going to need 8 rows. How many columns are we going to need? Well, let's count them out. We've got 3 atomic statements, so that's 3. We have the negations of 2 of those. We have not K and not E, so that's going to be 5. We're going to have this disjunction, G or E, that's 6. We're going to have this conditional, G or E, then not K, that's 7. We're going to have this conjunction, not K and not E, that's 8. Have the negation of that conjunction, 9. And then we're going to have the entire conditional, this antecedent and that consequent, 10. So we're going to need 10 columns. It's going to look a little like this. Now, in order to get everything to fit on this slide, I've had to sort of break the lines here in a way that's not very visually appealing. Don't do that on an exam. You shouldn't have to do it on an exam. If you absolutely have to, I guess okay, but try not to do that. I'm only doing it because it's necessary. Well, now I'm going to just follow the recipe. Oh, before I do that, notice that I put the atomic statements in alphabetical order, e.g. K. Even though if you just sort of looked at the statement from left to right, G is actually kind of the first one that makes an appearance here. But remember, we need to put these in alphabetical order, not the order in which they kind of appear left to right in the statement. So I put E first. Okay, now I need to start filling out columns. Column 1, I'm going to do the top half T's, bottom half F's. Okay? So that's groups of 4. Now I'm going to move over 1 column and alternate by groups half as big. Well, I just did groups of 4, so now I'm going to go do groups of 2. True, true, false, false, true, true, false, false. I'm going to move over 1 more column and alternate by groups half as big. Well, I just did 2, so now I'm going to do 1. True, false, and so on. And everything so far so good, because the column where I alternated by groups of 1 is also my last atomic statement, which is what it should be. If that weren't the case, then I did something wrong. That would be an indicator to me that I screwed up somewhere. Okay, let's do the compound statements now. Starting with not E, that's going to be easy. That's just the opposite of E. So 4 falses and 4 trues. And not K is going to be the opposite of K. So it's going to be false, true, false, true. That's pretty straightforward. Now let's do the disjunction, okay? G or E. Well, the 2 disjuncts are here in columns 1 or 2. So I'm going to do what I just told you. I'm going to look at those 2 columns. And with the disjunction, I'm going to look for the rows where they're both false, because the disjunction will be false there and true everywhere else. And as I look down, I can see that rows 7 and 8. 7, they're both false. 8, they're both false. So I'm going to put false for the disjunction on rows 7 and 8. And then everything else is just going to be true. I don't even need to look at the specifics of the rest of the rows. Okay. We do something similar for the next statement. This is a conditional. Okay. So the antecedent, I'm going to mark in blue, is G or E. The consequent, not K, I'm going to mark that in green. Now remember, with the pattern I'm going to look for with a conditional is true antecedent, false consequent. So I'm just going to look for true here, false there. And column 1, no, yeah. Column 3, no, yeah. Column 5, no, no, no. So 1, 3, and 5 I'm going to put false. Everything else is true. Let's do the conjunction. Where are the conjuncts? Right here in these two rows. The pattern I'm going to look for with conjunction is where both conjuncts are true, because everywhere else is going to be false. Where are both conjuncts true? Here and there. So I'm going to put a true in 6 and 8, F everywhere else. Now this is just the negation of the prior column. This is just not K and not E. So this is just going to be the opposite of that. That's going to be easy to do. False becomes true, true becomes false. And now finally I have the conditional here. I've got the antecedent in blue and the consequent I just marked in green. I'm going to look for the falsifying pattern. True antecedent, false consequent. Where do I see that pattern? Here and there. 6 and 8. True, false, and true, false. Those are the only two rows that have that pattern. So I'm going to put false there, true everywhere else. Okay. So now you know how to construct a truth table. What are the truth tables doing exactly? Why are we constructing them, and what are they doing for us? Well, think of it this way. We have a compound statement which is composed ultimately of atomic statements. Now, by ultimately, I mean the compound statement we're interested in might be composed of compound statements which are composed of compound statements, but eventually we're going to get down to the atomic statements. Okay? Now, we don't know of any of the atomic statements whether it's true or false. Okay? We just have no idea. We're just pretending ignorance on all of this. So what we're going to do is we're going to list off all of the possibilities. So even though we don't know what's true or false, we'll know that whatever the possibilities are, we've listed them on our truth table. Okay, and that's what we did when we fill out the atomic statements, and we make sure we get all combinations. So what the truth table will then show is that for each possibility, whether the compound statement is true or false, given that possibility. Okay, so for example, here's a truth table. Suppose our atomic statements were something like cats eat spiders and dogs are robots. Okay, and in that situation, our compound statement, if we were to read that out, would be something like, if it's not true that cats eat spiders if and only if dogs are robots, then dogs aren't robots. Okay, kind of a weird sentence to go around saying, but that's what the full sentence would be. Well, what we can then do is we can see that each row corresponds to some possible universe. You think of it as an alternate reality or an alternate universe or something like that. And in particular, row 1 represents the universe where cats eat spiders and dogs are robots, where both of the atomic statements are true. And in that alternate universe, our compound statement is false. Okay, the next row represents the alternate universe where cats eat spiders and dogs are not robots. D is false. And in that universe, the compound statement is true. The next row represents the universe where cats don't eat spiders, but dogs are robots. And the compound statement is also true in that universe. And finally, row 4, we have the universe where both atomic statements are false. Cats don't eat spiders and dogs are not robots. And in that possible world, possible universe, our compound statement is true. Well, not only does it let us do that, we can also answer questions. Before I get to that, let me point out. Well, actually, let me just stick with the order of the slides here. We can know things like any universe in which dogs aren't robots is a universe where the compound statement is true. Right? So for example, here are the universes where dogs aren't robots. And in both of those worlds, the compound statement is true. By the way, it's also eventually going to let us assess things like in any world where the premises are true, the conclusion is also true. which is how we're going to sort of eventually assess validity. So that's where we're going with this. Now it turns out that the actual real universe is one of the possible universes. And in fact, it's represented here on row 2, because in the real universe, cats do eat spiders. It's kind of gross, but they do. And dogs are not robots. D is false. So the second row represents the real universe that we're actually in. And in our universe, that compound statement is true. Okay, let's move on. One final topic, which is pretty easy. We can use our truth tables to assess whether statements are tautologies, contradictions, or contingencies. Now, it's often useful for us to know the range of truth values that a statement can have, right? And there's 3 possibilities that are going to be important for us. Statements that are always true, they're true in no matter what universe you go to, that statement is true. Okay, we're going to call that a tautology. Statements that are false, they can't be true, they're always false, we will call a contradiction. And statements that are true, can either be true or false, we'll call a contingency. Those statements are contingent. Now, by definition, atomic statements are contingencies. Atomic statements can be true or false. So all atomic statements are contingencies. They're all contingent. So if we're going to have any tautologies or contradictions, they're going to have to be compound statements. So here's an example. Here's a compound statement, P or not P. And you should be able to tell by looking at this disjunction that this statement's always going to be true. Why? Well, because a disjunction, the truth function for disjunction is that the disjunction, whole disjunction is going to be true if either one of the disjuncts is true. It only takes one disjunct. And because the 2 disjuncts are P and not P, one of them is the negation of the other one of these disjuncts is always going to be true. If P is true, that's enough. The disjunction is true. If P is false, well, then not P is going to be true. So no matter what you do, one of these 2 disjuncts is true, and so the disjunction is always going to be true. So this is what the truth table would look like. And you can see that no matter what you do, that disjunction ends up being true. A little more formally, in order to categorize a statement, what you do is you do a truth table for that statement, and then you look at its truth column, the column of T's and F's underneath that statement. If there's only T's, that's a tautology. If there's only F's, it's a contradiction. If there's both T's and F's, then it's a contingency. And in the last case, both T's and F's, it doesn't matter what the proportion is. Okay, it could be 1 T and 63 F's. It doesn't matter. Or it could be half and half. As long as there's a mixture of both, it's going to be a contingency. So in this case, that's our truth column for P or not P, and you can see it's got only T's. Therefore, it's a tautology. Now this statement is a contradiction, and you might be able to tell just by looking at it if you understand what the conjunction truth function is. Remember, a conjunction is only true when both conjuncts are true at the same time. And you can see because one conjunct is the negation of the other, they can't both be true. If B is true, not B is going to be false. And if not B is true, B is going to be false because they're the opposite. So there's no way you could get both of those conjuncts true at the same time. So that statement's always going to be false. And you can see that if we do a truth table, it'll look like this. Let's look at the truth column. It contains only F's, so the statement is a contradiction. Now let's do another example. It may not always be obvious. In the case of P or not P and B and not B, you could just look at it and tell. But you're not always going to be able to just look at a statement and tell. So let's do a truth table for this and figure out, is it a contingency, tautology, or contradiction? Well, here's the truth table. We've got these statements, fill out R and S. S or R looks like that. The negation is going to look like that. And now we're going to do the conjunction of those 2 things. And it turns out it's always false. Okay, if you do this truth table, we can look at the details. It's a conjunction. Here's one conjunct. Here's the other conjunct, and you can see there's no row where they're both true. It's false all the way down. So our statement is a contradiction. So that's pretty easy. When you're asked to categorize a statement with the truth table, you just do the truth table, you look at the truth column, and it's simple. If it's all T's, it's a tautology. All F's is a contradiction. Any mixture of the two is a contingency. And that does it for section 2.3 and for this video.